Hi, my name is Mansoor, Sheik-Bahae. In my group, we are engaged in a variety of experimental efforts ranging from laser cooling of solids, ultrafast photonics, lasers and spectroscopy, and semiconductor photonics. What you're going to see next is some highlights from our labs and from the students working in the lab in the current projects.
One of the main research topics in our group is the laser cooling of solids or optical refrigeration. This relies on an anti-Stokes material, in our case, a rare earth ion, which fluoresces at a slightly higher energy than which it is pumped by. This energy difference is due to lattice vibrations in the material or heat. By removing these lattice vibrations, we in turn are able to cool the crystal. To effectively cool the crystal, we need to have it in a high vacuum chamber where we can remove any heat load and condensation on the crystal. Using a high power fiber laser and a two-mirror multi-pass system to increase the absorption, we are able to cool the crystal below 100 Kelvin, approaching the temperature of liquid nitrogen. Not only do we want to cool our crystal, but we would like to cool something useful, a payload. This is done by attaching a thermal link from the crystal to the load. With the amount of fluorescence in our system, we must shield our load. By using a unique geometry in the thermal link, we are able to avoid the fluorescence from hitting the crystal. Using this design and other engineering feats, we are able to cool an arbitrary payload, in this case an IR sensor, to 130 Kelvin. The main advantage of optical refrigeration compared to other cryocoolers is that we create a vibration-free system. We hope that this technology will be beneficial to several applications in the future.
One application of laser cooling is radiation balance lasers, where fluorescence cooling can be used to offset the heat that is generated inside a gain medium, as we know, due to quantum defect and non-radiative processes. This heating is a limiting factor in high power operation, especially in solid-state lasers, due to the optical pumping, and leads to degradation of the efficiency, degradation of the beam mode, and instabilities at high power. So that very complex thermal management and beam resonators have to be designed. In radiation balance laser, the quantum defect is reduced because the pump is tuned to wavelengths longer than the mean emission wavelength, so that lasing and cooling occur at the same time, and this removes the need for heat sinking and other type of thermal management or adaptive optics to compensate for beam degradation and beam distortion. In order to do that, we use a very high purity cooling grade rare doped crystals. We build a laser cavity, multipass pumping in case of disk, and we characterize the laser output in terms of optical and thermal properties.
Another type of lasers that we are working on is the vertical external cavity surface emitting lasers, or VCSELs. But one of the main drawbacks of these VCSELs is the heat dissipation through the distributor break reflector, or DBR. That is one of the mirrors of the cavity, and this prevents the high output power operations. So at UNM we were the first to come up with a solution. We are using membrane external cavity surface emitting lasers, or MEXELs, and these MEXELs comprise of a semiconductor gain medium sandwiched between two heat spreaders that can be either silicon carbide or diamond due to the high thermal conductivity coefficient, and this allowed us to generate very high output powers. Another way to prevent the thermal rollover is to use the so-called in-well pumping technique, where we use pump wavelength closer to the emission wavelength of the lasers, and this reduces the heat generation in the active region and allows us to achieve again high output powers. One of the projects that we are working on is the sodium guide-star lasers, and this is funded by the Air Force Research Lab. And this in this, we will use maxills for sodium guide-star applications, where we excite a layer of sodium up in the sky, roughly 90 kilometers from Earth, and by collecting such signal, we can correct for the atmospheric distortion by using adaptive optics, and with this we can improve the resolution of the images in the ground-based telescopes.
In addition to high power operation, we have also investigating the mode locking of VCSELs. Typically, VCSELs are mode locked using searchable absorber, but we are researching curve-length mode locking of VCSELs. Here we rely on the nonlinear curve effect in the gain chip or a separate curve medium inserted in the cavity. When the intracavity intensity is high, the curve medium acts as a lens, and then in that case, we can say rely on the aperture, say no matter hard aperture, the inserted aperture or the soft aperture, the overlap between the gain pump spot and the cavity mode size. In that case, the laser are preferred to be operated in the post-operation. For the ultrafast experiments, we also have a Tesla oscillator and a regen amplifier to generate high-power femtosecond pulses. We have used them to generate high harmonic generation all the way to EUV and also terahertz pulses that can be used for spectroscopy, to probe carrier densities in semiconductors or even imaging.
Well, thank you for your attention, and please feel free to visit our website and check out our publication link to see what we are doing in more details. Thank you again.